Thank you very much for coming, everyone. For those of you who don't know me, my name is Ben Evans. So I'm one of the co-theme leads, along with Mark Whitaker, who's in the room somewhere, looking after the materials and manufacturing theme within the Zienkiewicz Institute. So for those of you who don't know what the Zienkiewicz Institute is, this is one of these kind of umbrella organisations trying to coordinate and provide opportunity for discussion, research collaboration across the faculty in data, AI and modelling. It's kind of built upon the successes of the former Zienkiewicz Centre for Computational Engineering, obviously taking the name of our famous Professor Zienkiewicz, who I'm sure everybody in this room knows a little bit about. The Institute is split into these 5 theme areas, and we thought it would be a good idea to have what we're referring to as our distinguished seminars, at least once a year in each of these themes. I think this is the first one, is that right?
Right, yes.
So the first one is in this area of materials and manufacturing. So we've invited Professor Emile, am I going to get your surname right now?
Greenhalgh.
Yeah. Pronounce the G.
Yes,
Okay.
yeah, I think, yeah.
So Emile joined Imperial College in February 2003, where he currently, according to his website, still lectures in material selection, composite design, testing, characterization and failure analysis. And he's the head of the Composite Centre there. Emile obtained his BSc in physics from Imperial College and graduated in 1987, and then worked at Kinetic, conducting research on a broad range of aspects of fibre reinforced polymers. He's published over 100 reports and papers in this field, and under the general theme of his work has been composite mechanics, understanding and predicting of the structural behaviour of composites. Since 2020, he has held the Royal Academy of Engineering Chair in Emerging Technologies. Over the past 34 years, Emile has built up a respected international reputation in composites. In particular, his research is focused on 2 areas. The first is damage tolerance and failure analysis, fractography of composites, and multifunctional composites, or structural power, which is going to be the main focus of today's talk. He has pioneered the development of structural composites, which have led the capacity to store and deliver electrical energy, and leads one of the largest groups in this field. I first came across Emile probably a couple of years ago as part of a UK aerospace research consortium meeting, which I was attempting to chair, where the 11 universities who form part of the Aerospace Research Consortium, of which Imperial and Swansea are both members, got a small slot. Welcome, Arnold. You can relax now. Where all the universities who are part of that consortium got to present a little bit of their work, kind of that feeds into the problem of sustainable aviation. And it was a fascinating session. But I remember when Emile gave his talk, thinking to myself, goodness me, I didn't know that was even possible. And if you can get that to work, that is genuinely transformative. And I'm sure there's a big if there.
Oh yeah, for sure.
Which is we're going to get covered, I'm sure, to some extent in the talk today. Possibly more importantly than any of that is that Emile is a season ticket holder at Tottenham Hotspur. So we commiserate you on the result last night.
I don't know
you
if
were
it's...
there at the match.
I was, yeah. I might be a bit hoarse from that.
You're in safe hands today.
Oh, that's
so
good.
let's give a big Zienkiewicz Institute welcome to Professor Emile Greenhalgh.
Great, thank you. Could I turn the lights down a bit just to get the images working? Can you all hear me okay? I wasn't sure if the microphone's working. Yeah, cool. Okay, well, thank you for this opportunity to talk about my research, and I think you're going to find it very interesting what we're trying to achieve with this area. Just to sort of focus on my background a bit. So I am from a traditional composites background. I worked a lot on failure and damage in polymer composites, and then moving to Imperial, I moved into more multifunctional materials and nano-reinforced materials. And as you'll see, the sort of development of multifunctional materials is quite dependent on the development of nano-reinforcement, carbon nanotubes, graphene, things like that. They allow us to have these multiple functions in the material. And so we came up with this concept, I think in about 2003, 2004, we started developing this area and came up with some prototypes. And it's now taken off. There's a lot of interest in what we're trying to achieve, this idea of structural power materials. So this is a material that does 2 things simultaneously, 2 very distinctly different things simultaneously. So I now have this Chair in Emerging Technologies funding from the Royal Academy of Engineering, which has given me 10 years to actually mature this technology. And so the aspiration of what I'm trying to do is get this technology industrialized, get industry to take this up and take it forward. But as you'll see, there's some tremendous challenges we've got to try and address. And in fact, a lot of the research up to this point has been trying to work out what are the questions we should be asking with this work. So let me first introduce you to the team. I lead all the work in the group, and my background is mechanical aspects of composites, polymer matrix composites. But one of the challenges in working in a multidisciplinary area, multifunctional area, is that you need to bring in people that are from completely different backgrounds. So I have colleagues that I'm working with. Anthony Kersenak is an electrochemist working on batteries and fuel cells. And then my colleague Milo Schaffer is an expert on nanomaterials, particularly nanocarbons, and using those materials both in electrochemical aspects and in mechanical aspects. Emiliano is his background is in nanomaterials again, but particularly thermoplastic materials. And then Ajit Panesar, some of you may know, he works on additive manufacture and also modeling techniques, so topology optimization, aspects like that. And as you'll see, modeling is going to have a really important role in trying to take this technology forward. And we have a number of researchers. Sang Nagayan works on multifunctional design, and then we have a number of PhDs that are working on various aspects. Ximing's working on the modeling, and I'll show you some of her work a little later on. Emily is developing on structural batteries. Elias is working on thermoplastic electrolytes. So I'll talk a bit about the idea of the issue of the electrolytes, and then encapsulation is being covered by Odysseus. So let me give you the sort of motivation for what we're trying to do. So you'll hear a lot about multifunctional materials. There's a huge area of work on having materials that have electrical and magnetic properties, for instance. But what we're particularly interested in is structural materials. So these are materials that carry mechanical load, which we've imbued with a second, quite different function. So this idea of structural power that I'm going to talk about, but there are also applications with sensing. So having a structural material that can sense its environment. Self-healing materials, this work at Bristol. Actuation, so materials that are structural materials but can also actuate under stimuli. And in even energy harvesting. So these are a range of materials that are starting to get interest. So rather than just having this inert structural material that all it does is carry mechanical loads, we're trying to develop a material that has added functions. So it's more efficient use of those materials. So what I ought to reinforce first of all is that we're really going beyond this idea of smart materials and smart structures. So there's a lot of work that's been going on for decades of embedding sensors or embedding batteries into structures. So for instance, this is some really nice work that's been done, the US Navy, been going on for about 15 years or so, where they've been looking at embedding lithium-ion batteries into aircraft structures, these are UAVs, and looking at that as a way of making more efficient structures. So this idea of embedding devices, embedding batteries into a composite structure is actually relatively mature. But what we're doing is really going beyond that. We're not trying to embed a structure, we're not assembling a product out of a monofunctional structure and a monofunctional battery. We're actually trying to imbue the same material to do two things simultaneously. So for instance, the carbon fibers that we use within our material, they carry structural loads. These are aerospace grade carbon fibers. But those same carbon fibers have lithium ions intercalating into them and out of them to add a battery function. So the technology and the challenges with this are much more immense than for just embedding a battery, for instance. But the rewards from doing this are enormous, and I'm going to sort of elaborate on that in a minute in terms of what achieving this idea of structural power materials is going to mean in terms of our day-to-day lives. But to give some context to what's really driven us this way is this whole issue of sustainability and the issue of energy storage and electrification of transport. So if you're looking at an electric car, the issue you have here is that you have a car that has a number of batteries in, but you need to put more and more batteries in to actually improve the range of the vehicle. But adding more batteries adds more mass, so you need even more batteries to be able to do that particular journey. And so, for instance, if you double the weight of the car by adding more batteries, then it actually, sorry, let me take that back. If you want to double range of the vehicle, you can achieve that by the same amount of energy by halving the weight of the vehicle. And so things like Tesla cars, for instance, about 25% of the weight of the car is actually the batteries. So you're expending 25% of your energy just moving the batteries from A to B. So that in itself is really not very efficiently using these materials. It's parasitic weight. In aerospace, this is even more of a problem. So there's been a really big drive in aerospace to go for this idea of a net zero aircraft, a long-haul passenger plane that's not using any aviation fuel by 2050. So the challenge we have there is that if you're using kerosene in an aircraft, about 30 kilograms of kerosene is required for each passenger. If we use batteries and using current battery technologies, which have an energy density of about 250 watt-hours per kilogram, you'd need 1,000 kilograms of batteries per passenger. So that's really just not feasible. So if you look at the conventional electrochemistry sector, they're really trying to push forward the energy densities of their batteries. And I've got a graph demonstrating this in a moment. But the issue with enhancing energy density is that you run into sustainability issues, you run into longevity issues. A lot of these very high energy battery technologies have relatively short lives. And there's also the issue of safety. So aerospace is a very conservative industry. If you try and get a new material onto an aircraft, you have to go through a lot of steps to demonstrate that it's airworthy. So really, we kind of felt that we need a radically different approach to how we store electrical energy on vehicles. And so instead of having that parasitic weight of the battery, why not use the structural material to actually have an intrinsic ability to also store the energy? So you won't need batteries. Your body of your car, the casing of your phone would store the energy that you need for use. And so we worked very early with Volvo with this concept, and they were very keen on this idea, and we've gone on to demonstrate that this technology is feasible. And there's a lot of synergies here in terms of the sciences. Although we're bringing together electrochemistry and composite mechanics, which are very different fields, there's a lot of parallels. So for instance, in electrical energy storage, carbon is widely used as one of the electrodes, or both of the electrodes in some instances. And in structural applications, we use carbon fibers. So immediately there's some synergy there. There's also this issue that carbon fiber composites that we use in aircraft structures are laminated structures, while batteries, again, are laminated structures. So we thought there's some synergies there that we could try and exploit with this technology. So let me share with you our aspiration for what we hope this technology will achieve. So first of all, as with any sort of lightweighting technology, the idea that you could have a material that does two things simultaneously is going to give us lighter vehicles, it's going to give us more spacious vehicles. So what we're trying to convey here, for instance, is that you no longer need this big pack of batteries in the car, there's a lot more space in the vehicle. So what we're showing here is you're charging the vehicle. So in lots of applications, this is going to give us lighter weight, reduced volume, more spacious applications. But we sort of thought there are things here that this technology is going to offer beyond those sort of conventional things that we think about in engineering. So one aspect we recognized is that a lot of products, particularly portable electronics, the actual form factor of that, of your phone, for instance, is actually dictated by the battery. So in a phone, for instance, half the volume of your phone is the battery. So if we could now get rid of the battery and using the casing of the phone, which is a structural component, but imbue that with the capacity to store energy, you could now have phones as thin as credit cards because you no longer have to think about where you put the battery. So that was something that we thought would be very attractive from a sort of consumer point of view, that suddenly it opens up this space of you can make very slender devices. But as an aerospace person, I was immediately thinking about what can we do in aerospace with this. And so where we started to recognize was that at the moment for aircraft, you have hollow wings. And the reason you have hollow wings is because you need to store the fuel there, be it kerosene or batteries. That's all stored within the wings. But now if the structure of the wing itself or the fuselage stored the energy, you wouldn't have to have hollow wings anymore. So you go to very thin wings, and so therefore you reduce drag, you improve the efficiency of the vehicle. But if you start moving to thin-winged aircraft, you run into air elasticity problems. So the whole aircraft would need to look different. You'd have to start to look at these box wing type configurations, for instance. And so one thing we recognize with this technology is that this is not something that we can just retrofit onto an existing product. This is going to need a sort of blank sheet of paper. It's such a fundamentally different way of using structural materials that you have to rethink everything from the blank sheet of paper. So as we started to think about how we could use these materials, what we started to see was that it offers localization of power storage, energy storage. So you can actually, rather than having the power source as remote from the actual usage of that source, you have an opportunity to bring everything closer together. So for instance, in the aircraft cabin, when you're sitting on your seat watching your entertainment screen, the energy that's driving that is actually coming off the engines of the aircraft. And if you took away the panels in an aircraft, you'd see enormous looms of wiring. So we thought, what about if we actually made the floor of the aircraft cabin out of our material, and then that would then power these seat back displays and the USB ports that we have on the aircraft. And I'll show you in a minute a study that we've done that demonstrates this offers a huge weight saving. But this is something we've recognized with this concept, that it offers an opportunity to localize where you store your energy for a particular application. And then kind of in the wider context of thhow we started to think about how can this go beyond transportation. And so one thing, sorry, how do I get rid of that? One thing we started to think about was infrastructure. So where you're looking at using solar panels on your house, for instance, at the moment you have to have a great big bank of lead acid batteries in your basement to store all that energy. But what about if you actually made the bricks of your house into batteries? So the building, the walls of the building would actually store the energy that you capture with the solar panels. So this is where we saw this technology going. So this is all the aspiration. We're nowhere near achieving these things yet, but we're trying to think about where could this technology take us if we overcome the challenges. And I'm going to talk a lot about what are the challenges with this technology. So let me focus on that cabins application that I spoke about. This is a paper that we published 2 or 3 years ago where we actually looked at, if we considered an aircraft, an A220 aircraft, and we thought about using the floor panels to store the energy, we started to think about what's the sort of levels of performance that we would achieve in the next 5 years or so. So we chose a modulus for the laminates of about 28 gigapascals, and we chose energy and power densities of 144 watt hours per kilogram, so that's a sort of almost half of that of a conventional battery, and a power of 29 watts per kilogram, which is sort of akin to what you get with a conventional battery. So those of you who are not electrochemists, these are 2 parameters that are often used to define energy storage devices. The specific energy is essentially telling you how much energy you can store per kilogram of material, and the energy is in watt hours. And the specific power is how quickly you deliver that energy. So that's watts or kilowatts per kilogram. Okay, so taking those numbers, we started thinking about redesigning the cabin, looked at all the electrical systems, the electrical demands on that system, and we identified that if we took an A220, put this system into the vehicle, using those performance targets, we'd get a weight saving of 260 kilograms of weight per aircraft. That was equivalent to about 500 litres of space saved. And we then translated that into CO2 reduction. So for that vehicle, it would result in 280 tonnes per year of CO2 reduction. And that's about equivalent to 1% of the annual CO2 emissions of a single A220 aircraft on its sort of typical flight schedules. So this was very attractive, and we, as I'll show you, we think cabins is one of the early adoption routes that we see for this technology. We've also done some other studies trying to understand how this technology could be applied to other areas in aerospace. And what we've been trying to do here is what are the target performances we need to achieve in our materials to actually offer a benefit. And that's helping us identify what are the routes of we need to take this technology. So there's a lot of interest at the moment in these types of vehicle, these autonomous air taxis. So the idea is that you could take one of these air taxis to fly from City Airport, which is in the east of London, to Heathrow, which is in the west of London. And if you took a taxi, that would probably take you about 2 hours. But if you flew, it would take you about 15 minutes. So these air taxis hold about 4 people. They don't have a pilot. It's all autonomous. And so various companies like Vertical Aerospace and Airbus are developing these types of vehicle. These are fully electric vehicles, and the challenge with these vehicles is that the battery technology is not there yet in terms of allowing them to have a significant range that's useful. So for instance, the City Airbus vehicle, this is probably a previous incarnation of the development of this vehicle. That has a range, or an endurance of 15 minutes with the batteries they're using at the moment. So we started to think about, if we took the batteries out and we replaced the structure with our material, what benefits could that offer, and what levels of energy density do we need to achieve? And so this is illustrated here, where we're showing for two different types of sources of energy: the conventional batteries, which is the black line, and using structural power material, which is the red line. And this is showing the relationship between endurance of the vehicle in minutes and the specific energy of the power source. And so the take home from this is that if you go for a fixed amount of energy density for your power source, by using structural power materials, you double the range of the vehicle. To put that another way, if you want to fly from London to Manchester, which is 240 kilometres, the conventional batteries would need to have an energy density of about 370 watt-hours per kilogram. And that's not a level that we're going to achieve in the next probably 5 or 10 years or so. For structural power material, you need less than half of that, 170 watt-hours per kilogram, which we haven't achieved yet, but it's sort of within reach. So the attraction in this technology is that it's something that actually will help us achieve electrification of transportation without needing the astronomically high levels of energy density that we need for batteries to achieve that. But let me focus on that a bit in terms of where things are with conventional batteries. Because you read a lot in the newspapers about new battery technologies coming out with horrendously high energy densities. So this is showing you a graph of all the different types of battery chemistries that are evolving and the ones we currently use. So things like lithium ion, for instance, you're familiar with. And this is showing you the specific energy, so how much energy it stores per kilogram, but also the energy density, so how much energy it holds per litre of material. So just to put that in context, for a Tesla car, sits at about 280 watt-hours per kilogram is the pack energy density. There's lots of these new battery technologies like lithium sulfur, lithium air, so this gives you an idea as the sort of levels of performance that those offer. However, if we want to go to a fully electric airliner, those batteries would need to be up here. So if we wanted to have a replacement for the A320, for instance, to fly from here to Greece, you would need to have an energy dense, a specific energy in excess of 1600 watt hours per kilogram. And we're currently at 280 watt hours per kilogram. And to give you a bit more context here, if I had a piece of TNT, that has an energy density of 1160 watt hours per kilogram. So we're trying to persuade the aircraft industry to have a block of material which is even more energetic than a block of TNT. So this is really putting into context the challenges associated with going for a fully electric, conventional battery-powered airliner. So we thought, why don't we explore what happens if we use structural power material in this context? And so what we started to think about was, what about if we had an airliner which was a hybrid of conventional batteries and structural power material? So the wings, the body of the aircraft would store the energy, and you'd had to add some more batteries to give you all that energy you'd need. So this graph is kind of capturing what we found with that. So we looked at different energy levels for our structural power material, and then these lines indicate different energy densities for different battery technologies. And then the horizontal axis showing you the mass of conventional batteries you'd need to allow that airliner to fly from here to Greece, for instance. So for example, you could use, say, 17 tons of conventional batteries at 700 watt hours per kilogram, which is, almost 3 times higher than the conventional technology, but certainly not in that sort of really high 1500, 1600 that I mentioned earlier. And structural power material that's at about 300 watt hours per kilogram. So what we were starting to see with this technology, if we can get it up to the higher energy levels, it starts to become an enabler for fully electric aircraft. But those of you working in aviation recognize that the reason that we've had this sort of change now to hydrogen is specifically because of that issue of the battery technology. But what we see with structural power is that it doesn't necessarily have to be used with conventional batteries. It could be hybridized with hydrogen power. So the idea, for instance, is that you'd have a hydrogen-powered propulsed aircraft that powers the engines, but then you'd use structural power materials to run the cabin and things like that. Okay, so let me talk a bit about the sort of where things are in terms of structural power materials and focus in on the technology that we're working on. So if you talk to an electrochemist, they'll show you this type of plot, which is a Ragone plot, which is showing you the relationship between specific energy and specific power, or it could be energy density and power density. So if you're looking at volumetric terms. And these are the different types of devices. So batteries have high energy density. Sorry, let me put this into a pointer. So batteries have high energy density, but they are very sluggish because they work by chemistry. There's a chemical reaction going from charged to discharged. And so thermodynamics starts to become very important for batteries. So the batteries, although they can store a lot of energy, and fuel cells are even worse, even better in terms of how much energy they store, they're very slow at delivering that energy. The other end of things are capacitors, so electrostatic capacitors, the sort of thing you might have used at school. Those deliver energy really quickly. They have a specific power in the order of 10 to the 5, 10 to the 6 watts per kilogram. But they can't store very much energy. So those capacitors tend to be used in sort of energy weapons, lasers, where you want to deliver energy really quickly. What we focused on are known as supercapacitors. So supercapacitors are essentially a type of capacitor. So if you might remember from school, the way a capacitor works is you have 2 plates which are a certain distance apart, and the closer you get them together, the higher the amount of capacitance you have, and then the amount of charge you can store is related to the surface area of those plates. So what happens in the supercapacitor is we make that surface area really, really large by making the surface really tortuous. So it's very high surface area. And then the charges are actually stored at the interface between the electrodes and the electrolyte. So rather than being millimeters, they're actually the order of nanometers apart. So by doing that, you can develop supercapacitors which can store considerably more energy than a conventional electrostatic capacitor. But they're not going to be as good as batteries in terms of how much energy they store, because there's no chemistry going on. It's purely a physical process of moving ions within the material. But what you can do is make hybrid devices that have got a bit of battery chemistry going on and a bit of sort of electric double layer, so that's the supercapacitors. So things are things like asymmetric supercapacitors and hybrid supercapacitors, which actually have a battery electrode and a supercapacitor electrode within them. So when we started working on this area, we started thinking about what should we go for? And we thought there are some problems with batteries, and I'm going to give you a comparison in a minute. So we really focused on supercapacitors as the way we went with this technology. So we focused on supercapacitors, and as you'll see, we've done a lot of development. We've taken this technology forward quite considerably. But while we were working on this, we started speaking to people in Sweden, in KTH and Chalmers, in Stockholm and Gothenburg, and they've started working on structural batteries. So a little behind us, and so they've started developing that type of technology. I'm going to focus on structural supercapacitors because it's what we're doing, but there's a lot of challenges associated with both these devices which is common to both. And so the things that we deliver with our technology is going to help the people in Sweden with their developments. So just to give you an idea of where we are, a conventional supercapacitor will store about 5 watt-hours per kilogram and has a power density of about 5 to 10 kilowatts per kilogram. We're sitting at about 1.4 watt-hours per kilogram and 1.1 kilowatts per kilogram. So we're not as good as a conventional supercapacitor, but then we have a material that you can build a table out of, for instance, which you can't do with conventional batteries or supercapacitors. This is where we expect to get to over the next few years, pushing up the power and energy density, but our material also has mechanical properties. So this is the Young's modulus and shear modulus of our material, and it's getting towards what you get for a conventional composite. The battery technology, they have much higher energy density, so they're currently at 45 watt-hours per kilogram. If you remember, a conventional lithium-ion battery is 280 watt-hours per kilogram, but this is increasing rapidly. That's the number they've published. They're now up into about 100 watt-hours per kilogram in terms of their energy density. So we're getting very close to approaching a conventional battery or a conventional supercapacitor. But the added thing that we can offer is a capacity to store but carry mechanical load. So we don't need to be as good as a conventional battery or supercapacitor in what we're doing. So let me explain a bit about how our devices are assembled. So essentially, for a conventional supercapacitor, you have 2 plates which have very high surface area, and those are electrically conductive. And then you have a separator layer which is electrically insulative but allows ions to move through the material. Then between those 2 plates you have an electrolyte. So that electrolyte consists of a liquid that has ions in it, cations and anions. And when you charge the device, you force one set of charges to move to the positive plate, the other set to move to the negative plate. And so it forms what's known as a double layer. And because you've got very high surface area and the charges are very close together, you get very high energy storage compared to a conventional device, conventional electrostatic capacitor. So that's a conventional supercapacitor. What we've done is we've taken carbon fiber fabrics and we've recognized that carbon fibers don't have very much surface area, so we've done stuff to them to increase the surface area, and I'll talk a bit about that in a minute. We have current collectors, because although carbon is electrically conductive, it's not as good as something like copper or aluminium, so we have to put a current collector on there to help with that. We have an electrolyte, and so rather than that being a liquid electrolyte, it's actually a blend of a structural material and an ion transport material. What we use is something called an ionic liquid. So an ionic liquid is probably the best way to think about that is it's a ionic material that's a liquid at room temperature. So if you took table salt and you took it up to 800 degrees C, it would become a liquid, and you could use that as an electrolyte because you've got sodium and chlorine ions. If you apply a voltage to that, it will force those ions to move, and you can store charge. Ionic liquids are an ionic material which is liquid at room temperature, so you can use it as an electrolyte. And so what we use are, they're two organic, an anion and a cation, which are organic. And then we have a separator layer, which is either a glass fiber fabric or some sort of non-woven ceramic veil. And so that allows us to produce the devices. So let me talk a bit about the difference between supercapacitors and batteries and sort of explain the different research challenges associated with those. So supercapacitors we felt were a more low-hanging fruit in terms of this whole idea of structural power. There were some big challenges with batteries that we were worried about. So supercapacitors, you tend to use them where you want high, rapid delivery of energy. So things like if you suddenly lose power in your laptop, for instance, there's a supercapacitor that kicks in that provides an emergency power source to power down your computer. It can be used for capturing energy, like regenerative braking, things like that. So it's a technology that's not as big as the battery technology, but it's certainly a stepping stone towards what we're trying to achieve. So giving you a comparison, lithium-ion batteries, they give high energy but low power. Supercapacitors are the other way around, low energy, high power. As we're all familiar with conventional batteries in your phone, they have a limited cycle life. You know, your batteries die after a few years' use. So a lithium-ion battery, it's the order of 1,000 cycles. And that's because you're essentially doing some chemistry. You're basically, when you charge and discharge, you're actually changing the chemistry of your material. With supercapacitors, they have life in excess of 1 million cycles. So they're very attractive from that point of view. Battery materials are very sensitive to moisture, and even oxygen that's in the air can permanently degrade battery materials. So from the perspective of making a wing, for instance, out of a battery material, that presents some very big challenges. With supercapacitors, they're less sensitive to moisture. We kind of saw this as an easier route to get industry interested in this technology because we can potentially get rid of the moisture once you've made the device. Another problem with batteries is that when you charge the material itself expands. What you're essentially doing is moving lithium ions into the carbon, and that actually pushes the carbon planes apart and makes your material expand. So if you have a material that you're charging and discharging causes it to expand and contract, and you want that material to be your mobile phone casing, for instance, that's going to present some challenges. That's not an issue for supercapacitors. There's no expansion or contraction that goes on during charging. So in terms of research challenges, those charging issues, in batteries, the swelling and contraction you get are going to offer challenges in terms of managing the strains that can develop in the material and potential damage that's induced. But for supercapacitors, that swelling is not a problem, but the interfaces that we develop, and I'll talk a bit about that in a minute, those become important. Batteries are very moisture intolerant, while it's less of an issue for supercapacitors. So what becomes the research challenge in batteries is actually having enough active material in the device. While for supercapacitors, we're trying to find ways of getting us higher energy densities in the material. In batteries, you're looking at having robust electrical contacts, but in supercapacitors, because everything's driven by how quickly you can deliver the energy, then the resistance, the electrical resistance of the material becomes really important. And so what we're striving to do with supercapacitors is reduce the electrical losses in the current collection. So I'm now going to sort of talk about the different themes of the research that we're doing. And in developing this research field, and the nice thing about working in this area is that there's a huge amount to be done. We're not filling in gaps, as with often conventional research areas. We've got this whole empty field that we're trying to build up. And so we've partitioned this into 4 themes. So there are 2 themes which are kind of scientific driven. So actually developing the electrodes, the electrolytes, the constituents in the material. And then there is the theme associated with actually the assembly, the fabrication, the characterization of these materials. So we see these as scientific challenges. But I'm an engineer at heart, and I'm quite keen on the engineering aspects of this technology. So I'm not so interested or excited by discovering new materials. I'm interested in how I can turn these materials we've discovered into something useful. So modeling is a really important aspect of this, because we recognize to get this technology to mature, to get industry to take it on board, we need to have robust, reliable models in order to build up this technology. And then the final aspect, theme 4, is really related to scale up. So rather than just making one device that's about 4 by 4 centimeters, we want to understand how we can build a product, so an aircraft wing or a car body, out of this material. So before I talk about those themes, I just want to flag up a paper that we recently published, I think it was last year, where we looked at all the literature on this area. And this really gave us a lot of insights that I'm going to touch on as we talk through the presentation. We looked at all the literature that was out there in terms of performance of the electrolytes and the devices. So this is looking at capacitance against Young's modulus, for instance. And also looked at some of the engineering issues. So where are things with the modeling, where are things with the current collection, things like that. And that really came up with a series of recommendations for this technology that I'm going to be touching on as I go through these 4 different themes. But to sort of help break this talk up, I thought maybe at this point I could field any questions you have on what I've covered so far before I dive into the individual themes at all. So, yeah.
I was just wondering, there's obviously, when you design a composite, normally there's a lot of rules in the design that you have to follow to get the directional spread.
Yeah.
And also there's a lot of challenge when you make composites, they're quite fussy things to make. Does this sort of technology add significantly to those sort of...
It does. It does. I mean, so working in composites, we have to worry about balancing the layup. So you have to have, you choose a stacking sequence where you've got particular modulus, elastic requirements. You have to make sure that the stacking sequence is mirrored at the midplane. You have to ensure you've got the same number of angle plies, plus or minus direction. And so you end up with a laminate with 0 B terms. So that's the mechanical aspect. The problem that we have with structural power materials is that they're also batteries or supercapacitors. And so a battery has an anode and cathode, which are different. And so therefore, if we just stacked an anode, a separator, and a cathode, we'd have a laminate which was unbalanced. So we're starting to think about things like 3 electrode cells, where we have 2 anodes and a cathode in the middle. And so it's effectively 5 layers with the 2 separators as well, which isn't ever done in conventional batteries. But it's something that we think we might have to do just to deal with those balancing rules that we have. And then in the manufacture, I'll talk a bit about that in a minute, but the manufacturing, the biggest challenge there is keeping it in a dry environment. So there's a huge range of knowledge on composite manufacturing routes, and what we're trying to do is understand how we can adopt those to produce these materials in a dry environment. Thanks. Any other questions at all? Yeah.
Is there any relationship? Sorry, any relationship between the mechanical and electrical functions? So, for instance, if you're straining one of the components mechanically, does it change its storage or discharge?
Yeah, this is something with the supercapacitors that doesn't happen. It's completely uncoupled as long as you're in the elastic regime. We certainly have seen evidence that if you go beyond the elastic regime, you start to damage the material, it will change the electrochemical performance. But for batteries, there's some really interesting stuff. And this is, if you look at the work at Chalmers and KTH, so that's Zienkiewicz and ASP at those institutes, they've recognized that because of this issue that when you intercalate the lithium ions in, the material swells, you can actually start to use it as a sensor, you can actually use it as an actuator. So you basically, they've set up a configuration where you charge the device and that actually acts as an actuator. It's incredibly slow because it's a sort of diffusion-driven process, so it takes several hours to actuate, but it's carbon fiber, so it's very stiff, and the voltages you need, if you try to use piezoelectrics, you're looking at hundreds of volts to do actuation. This just uses 3 volts to do that actuation. So that's an interesting thing. But they've also actually found there's a route to do energy harvesting with these materials. So essentially, there is a relationship between the strain energy in the material and its voltage response. So if you cycle it in the right way, in combination with the elastic deformation of the device, you can turn strain energy into electrical energy, and so use it as an energy harvester, basically. But this is all very low TRL, sort of proof of concept stuff. But it's certainly something that we've seen, and we see it as a way that this technology could perhaps go beyond energy storage, I think. Okay, yeah.
We're working on some similar stuff, but it's more related to the defense, especially the supercapacitors, in a way that is, I presume you have heard about the magnetocumulative effect. That is the magnetocumulative effect.
No, I'm not familiar with that, sorry.
Producing by explosion, charging the supercapacitor to produce the electromagnetic pulse.
Oh, I see, yeah, yeah.
So this is something that we are looking now, and with the electrochemical department here, the group that we have, we are also looking to implement a little bit of that. I was just wondering whether you will go into the details, like how, like a material, what you've done with carbon nanotubes, like encapsulating, like for example, we are trying to encapsulate the cobalt and to see what we can do with that, to say in a way, or the doping with the boron and something like that.
Yeah.
Did you have any reflection on how this changed, to say, the behavior of the composites?
Yeah, I will talk a bit about the constituents we're using. I mean, we're using carbon aerogel. The battery people in Sweden are using lithium-ion battery chemistries and things. But we are going now beyond the double-layer chemistries, double-layer devices, and going into hybrid ion capacitors and things like that. And so, but I'll touch on certainly some of the other chemistries and things that we're exploring with this. Yeah. Okay, so I'll press on then. So let me first of all focus on the constituents. So this is the first theme in the research we're doing. This is looking at the electrode development. So the role of the electrode is to store, is essentially, that's where the high surface area is that stores the energy. So we want a material that's very high surface area, but it also has to have mechanical requirements. And so the key sort of research question we have is, can we increase the surface area without degrading the mechanical properties? And if you look at the literature, and this is in the review paper that I mentioned, there's lots of different strategies for that. So you can grow nanotubes on the surface, you can put graphene on there, you can put, people are putting graphene onto aramid fibers and things like that. What we focused on is carbon aerogel as a route for doing this, and I'll talk a bit about that in a minute. The other route is actually to introduce a little bit of chemistry in there, so you get some battery chemistry, and this is known as pseudocapacitance. And so there are various different types of material. Manganese dioxide is often the commonest used material to induce some degree of chemistry in the material. but there's a lot of work looking at copper oxide, zinc oxide, and these carcagenides. So these are selenium-based compounds which offer pseudocapacitance. So the idea here is that you grow this active material onto the fibers, so that increases its capacitance. But you can also see if you start to get interlocking between these sort of spikes, for instance, that's going to give you improved mechanical properties as well. So that's something we're exploring with this technology. But what we've really moved on to is carbon aerogels. And just to explain what carbon aerogels are, these are effectively amorphous nanocarbon foams. So it's essentially produced by infusing a precursor into the carbon fiber fabric, and we're just using conventional aerospace grade carbon fibers, and then you pyrolyze that to turn it from a resin, so it's effectively a phenolic resin, into a carbon aerogel. And so this is an image showing you, this is a carbon fiber which is about 7 microns thick, and then this is the carbon aerogel within the matrix space between those layers. So carbon aerogels are used widely in the conventional electrochemistry field for supercapacitors and even batteries. The problem with it is really brittle. But the nice thing about using the carbon fibers is they act as a scaffold. So rather than having a powder, the carbon aerogel is supported by the carbon fibers, and we can produce laminates. I think the largest we produce is an A4 size laminate, which is continuous carbon fiber with a continuous aerogel throughout it. So you have this aerogel, and then you can start to put other materials onto the aerogel to improve its energy storage capacity. So this is kind of showing, this is a laminate we've made. Zooming in, you can see the aerogel structure. And then we've done some comparative studies. This is showing you a baseline composite, so this is a structural resin with carbon fibers. This is a structural resin with carbon aerogel on the carbon fibers. So we're maintaining the same mechanical properties, modulus. If we use the multifunctional matrix, we get a drop because the multifunctional matrix, as I'll show you, is much softer. And then we did a desized version as a sort of control. However, the problem that we've encountered, and which is what we're addressing at the moment, is that carbon aerogel process damages the carbon fibers. And so we're now exploring how we can get around that problem, the fact that the carbon fibers are being damaged by the process of making the carbon aerogel. So we do have other strategies for producing electrodes. We're looking at using carbon nanotubes, for instance, putting those onto the carbon fibers as a way of improving the electrode development. So I would say on the structural supercapacitors, the actual electrode development is quite advanced. But where the really big research challenge is on the electrolyte. So the nice thing about the carbon aerogel is that we've identified the carbon aerogel is actually stiffer than a conventional epoxy. The carbon aerogel has a modulus of about 25 gigapascals. A conventional epoxy has a modulus of about 5 gigapascals. So we actually think the aerogel could be used to enhance mechanical properties of the composite if we can get rid of this degradation problem. And so that synergy there between mechanical and electrochemical is really attractive. It offers us a way of actually getting this technology to go beyond just a rule of mixtures. With the electrolyte, this is more challenging because we want a material that's mechanically good. It's rigid, so it can carry mechanical loads. It can transfer loads between the fibers, but it's got to allow the ions to flow between the fibers. So conventionally, electrolytes are soft, they're liquids or even gels, and they allow ions to flow. If you have a rigid material, it's difficult for those ions to move. So the approach we've taken, and we have some aspirations in terms of performance we want to achieve. So we want a Young's modulus of the electrolyte to be beyond a gigapascal, and we want the ionic conductivity to be beyond 1 millisiemens per centimetre. The approach we've taken has been to mix epoxy resin with an ionic liquid and to produce this biphasic structure. So this is showing you the microstructure of that material. We've washed out the electrolyte and it's just left the sort of porous structure of the epoxy. And what we've been doing has been modifying the proportion of the ionic phase and the structural phase to modify that microstructure. So in the review that I showed you earlier, we've looked at these different strategies, and it really shows us that the dual phase electrolytes, which are the open boxes here, or the are the boxes, and then the green ones are one route, which is polymerization-induced phase segregation, or the open boxes are reaction-induced phase separation. Those are two sort of chemical routes to produce this biphasic structure. That looks the most attractive route to get a combination of ionic conductivity and Young's modulus. So that's really where we're pursuing things. But everything there is to do with looking at thermoset materials. So thermosets are polymers where you mix two constituents together that react to produce a resin. But the problem with those sorts of materials is that they are very difficult to recycle, they tend to be brittle, and they actually take a long time to process. So there's another sort of technology associated with polymers called thermoplastics. So thermoplastics allow you to have formability and they're potentially recyclable. So we have effort at the moment to try and look at getting thermoplastic structural electrolytes that are rather than thermoset structural electrolytes. So the challenges here are that the processing temperatures for conventional high performance thermoplastics are enormous, 350 degrees C. So those high temperatures are going to be problematic in terms of producing a material which has functions, because a lot of those functions are going to be damaged by excursions into those temperatures. Producing that biphasic structure in a material that you're processing at those temperatures is also going to be very challenging. And thermoplastics, although they're quite tough, they tend to be very difficult to bond things to them. So things like polyethylene is a thermoplastic that's notoriously difficult to bond things to. So if we want to assemble a device where the layers are bonded together, that's going to be challenging. So we have various strategies that we're looking at to try and achieve a thermoplastic structural electrolyte. And so the attraction, the main driver there is that thermoplastics can be processed quickly. So we could start to get this technology into applications where the manufacturers want things to be made quickly, like portable electronics and automotive applications. It also means that it's a potential route to recycling of these materials as well, because thermosets are very difficult to recycle. Everything's been kind of locked together. With thermoplastics, you can melt them, you can recover the constituents. So that's one of our motivations for going down this route of thermoplastic structural electrolytes. And then something that becomes very important, so as a composite person, I'm always familiar with, we have fibers, we have matrices, that's two constituents. You put them together, you introduce a third constituent, which is the interface between the fibers and the matrix. And you find in composites that it's those interfaces that dictate a lot of the mechanical properties. With structural power materials, it's actually the interface that dictates the electrochemical properties as well. So designing the interface is going to be really important. And that's actually at several levels. We want to design the interface at the fiber matrix level. So this is showing you some carbon fibers with a multifunctional matrix on the surface. But also you have the interface between the electrodes and the separator. And again, there's conflicting requirements there. That interface needs to allow ions to move across it, but it also needs to be rigid to carry mechanical loads. So these are two aspects that we're very much focusing on at the moment, trying to address that. Let me move on to the separators that we're working on. So the separators, the role of the separator is to stop the electrodes touching each other so you don't get a short circuit. So they've got to be lightweight, but they've also got to offer some structural capacity. And so we have a wish list for those, and we're looking at commercial separators and new types of separator to try and take that forward. Separators are something that we thought would just be an off-the-shelf solution, but it doesn't turn out to be. We need to do some actual research to come up with new types of separator for our materials. So let me move on to the aspect of device manufacture, the architectures. So I spoke to you about structural batteries. I touched on that and focused on structural supercapacitors. The problem with supercapacitors is that they have low energy density. So we're now trying to see how can we solve that problem. So we have a PhD that's working on devices called hybrid ion capacitors, where you basically take a battery electrode and a supercapacitor electrode, bring them together to make this hybrid device, and Emily has already started making those, which will give us 4 times the energy density of a supercapacitor, but still keep the same amount of power density. So it immediately opens up more opportunities for this technology. But now I want to move on to the manufacture of these devices. And as I said before, we're trying to adopt conventional composite routes and see if we can modify those to take things forward. But there are a lot of challenges there. We need a moisture-free environment, so we're starting to use glove boxes. You're often presented with a multi-matrix composite, because we wouldn't make a final product that's entirely made from structural power material. We would have maybe the exterior skin out of conventional composite and the interior as the structural power material. So we've got to learn about making hybrid materials like the way. The processing conditions are potentially an issue because high temperatures, high pressures can damage the functional properties. Composites, we're very used to drilling holes in them, but we don't like to drill holes in batteries and things. So that's something we need to try and resolve. And there's the issues with curvature. And then if you have a product that has a multifunctional region and a monofunctional region, you've got to get load transfer across that region. So let me talk through how we make our devices and show you some of the challenges that that's presented. So we take the individual electrodes and we infuse them with the precursor for the carbon aerogel, do the pyrolysis to produce the carbon aerogel, put on the current collectors, and then we take the separator and we film a layer of structural electrolyte onto that. So we assemble that whole device, consolidate it, and cure it to produce the final device, as shown here. And then, but that final device, there's carbon fiber layers there which are electrically active. We can't just leave that out on the desk. It needs to be encapsulated. So the next stage is the encapsulation of that device within an electrically insulative layer. So we've been working on the fabrication issues and we've met some challenges. So the really nice microstructures we can produce in the bulk of the bulk production of the structural electrolyte, if we try and put that into the device, we lose that microstructure. So to address that point, we've got a project, an EPSIRC award, which we started in about a year ago, in fact, with Bristol and Durham, on called Realising Structural Power, and this is addressing the manufacturing challenges. So we have Natasha Shishova at Durham, who's working on the development of the structural electrolyte, but in sort of partnership with that, the group at Bristol, so this is Dmitry Ivanov, is working on how to fabricate these devices. So how to not just develop the matrix on its own, but to make sure that matrix is processable. And then from the Imperial perspective, we're working on current collection and encapsulation issues associated with this. So all these things feed into each other in terms of producing a final device. So moving on to characterization, let me just sort of talk you through how our technology has developed. So we've taken this Maxwell supercapacitor as our sort of baseline conventional device, and that has a energy density of 4.7 watt-hours per kilogram and a power density of 4 kilowatts per kilogram. And then we started in 2006 or 7 making the first devices. The energy density and power densities were ridiculously low. although mechanical properties were pretty good. But this is really just to demonstrate the concept. And what we've been doing over the years has been looking at new types of device technology, different types of electrodes and electrolytes, to come up with a better performance device. And we started to recognize there's kind of two types of device here. There's the fully structural device, where you have a structural electrolyte that allows you to carry mechanical loads. Or there's a semi-structural device where you're using carbon fiber electrodes, but you have a liquid electrolyte. And the attraction there is that although that type of device wouldn't be able to take shear loads or compression loads, it could be used under tensile loading conditions. So where we are now is a structural device of 1.4 watt-hours per kilogram and a power of 1.1 kilowatts per kilogram. So in developing these materials, we've kind of tried to understand what's the landscape for the work going across the world in this. And in putting that review together that I showed you, one of the things that came out of that review is that there is no protocols, no testing standards for these types of material. And this is actually the biggest hurdle to get industry to adopt this technology. So the problem here is that, first of all, if you're trying to characterize these materials, if you want to characterize the electrochemical performance, you use this little 10mm disc, either a coin cell or this is called a swage lock. You build your device and you characterize that at that very small scale. If you want to do a mechanical test, you have to have a specimen which is probably about 10 centimeters long, a centimeter wide, different scale. And so the problem is that if you're claiming that your material is multifunctional, but you've characterized the electrochemical performance and the mechanical performance on different size coupons, it's not really credible that you can say this is the multifunctional performance of my material. So that is something that we're trying to address. And what feeds into this is that ideally we'd like a test coupon that we can do mechanical testing and at the same time do electrochemical testing. And no such configuration exists at the moment. So this is part of the problem with the protocols. And then on the reporting, this is something that's kind of opened my eyes a bit in terms of electrochemical reporting. If you look at the headline numbers that are reported in electrochemical journals in terms of performance of the material, everything's normalized by the mass of active material or the mass of the electrode. But from the end user point of view, where you've got a piece of material on the table, you want to know how much energy you can store in that, you need to report that in terms of the device normalized data, so the mass of the device. So that is something that, again, needs to be addressed in terms of reporting this technology. So we're currently, I've got together all the lead people working in this field, and we've started to put together a sort of best practice and protocols for this technology. And what we've recognized is that you can characterize things at three different scales. You can look at the constituents like the fibers or the electrolyte, and you can characterize that using an electrochemical test, which is different to a mechanical test. And I think that's acceptable to do that. Then at the device level, you have to characterize that material in the same coupon electrochemically and mechanically to be able to say this is the multifunctional performance. And then another level will be components, where you assemble lots of cells together and start to talk about the performance of that. So moving on to the sort of data that's out there, let me just show you some of the results with that. And this is showing you an example of some of the data that we've collated from all the other researchers that worked in this area. So this is showing you specific capacitance against Young's modulus for the shapes correspond to different types of electrodes and the color corresponds to different types of electrolyte. But these ones are perhaps less interesting because these ones are using a liquid electrolyte, which is not really a structural power material. It's just a structural electrode that's in a liquid electrolyte, so it's kind of semi-structural. Perhaps what's more interesting is what we call a structural device that uses a structural electrolyte and it's normalized by the device mass. So when I looked at all the paper that's out there, some people only give the performance normalized by active mass or electrode mass, and some people only report device mass. And so I couldn't compare those different data sets, which was very frustrating. But this is showing you some of the different work that's been done in this area, the different types of chemistries that people have used. And then this is showing some of the data that we've produced, the carbon aerogel. And that looks to be one of the best performing devices that are out there. Let me now move on to probably the theme that's probably most interest to you, which is the modeling aspect, so theme 3. And as I said, this is something we're really focusing on at the moment because we see it's vital to take this technology forward. And the way we're addressing this is looking at modeling at several different scales. So we're looking right down at the micro scale, where you're having to deal with almost molecular level behavior, where we're looking at the storage of the charge at the electrochemical interface, for instance. We're looking at sort of multi-physics modeling to capture modeling of mechanical and electrochemical in the same type of modeling code. And there's also a sort of design aspect as well, as how do you design a product with a combination of conventional composites and multifunctional materials. So I'll touch on each of those levels. So one of the first things we started embarking on is, having worked with the chemists, everything they're doing is very much experimental. They mix the constituents together, they produce a microstructure, they change the performance, it changes the microstructure. But we never really knew what's the perfect microstructure that we want for our device. So we thought modeling would be the approach to achieve this. So we want to produce a sort of representative volume element of our material, and that volume element has to have a functional requirement. So it has to allow ions to move, say, horizontally through the material. But at the same time, it's got to do a structural requirement. It's got to carry mechanical load. And so the idea here is that you would have this optimized representative volume element that you would essentially build your electrolyte out of to produce your structural power material. So I should stress I'm not a modeler. I'm exclusively experimental in my background, but I'm working very closely with modelers to try and, they are being guided by my observations to motivate their model development. So this work was done with Ajit Panesar at Imperial. And so we used topology optimization to come up with what is the optimum motif for our microstructure to give us, say, the balance between mechanical loading in tension or in shear with maximizing ion flow. And so the way we did this was to look at different volume fractions of those two phases, the ionic phase and the structural phase, looked at different volume fractions of those, but also different weight fractions in terms of the functions. And we plotted this as a Pareto front to show either very high, so we've done the reciprocal of each of those parameters. So this end is showing you high electrical ionic conductivity. This end is showing you high mechanical properties. And so we've got this Pareto front, which is showing these are the solutions that give us, for a particular weighting between those two functions, the optimum solution, the lowest weight solution. And we compared that to a well-known structure called a Schwarz-P structure, which is recognized as providing a balance between transport and structural aspects, but it's an isotropic configuration, so it has the same transport in all directions. What we're interested in is only having maximizing transport in one direction and mechanical in the other direction. Now, what I thought was really exciting about this was once we'd done the topology optimization, come up with these solutions, we 3D printed them, as shown here. And we then characterized those in the lab. We looked at the mechanical properties and the electrochemical properties, albeit at a much larger scale. So these solutions were scale independent, and we were not really capturing some of the sort of micro scale physics that could happen. And that allowed us to demonstrate that these solutions were credible. So this was an exciting piece of work that we're really taking forward now, and we've started to look at the concept of what about doing multi-scale topology optimization. So if you consider one of those unit cells shown here, this is one of the unit cells that's optimized for shear loading. If you start to scrutinize that microstructure, there are some regions that are seeing high direct loads and some regions that are seeing high shear loading. So what we're able to do is have a library of different motifs and then implant those into this larger scale motif to give us an optimized structure. So using this, we're able to actually demonstrate, and I could show to the chemists, this is the microstructure I'd like you to make. And so that really is helping us move this technology forward because we know what we need to achieve in terms of the structure of the electrolyte. Let me go up to a larger scale now and look at the sort of multiphysics modeling that we're trying to achieve. So the idea behind this is that in order to get to the point where we can start to design using models our products, we need to have modeling tools in place. And we recognized early on that actually one of the first steps is modeling the consolidation process. So here you've got two electrodes and the separator, and then when you're consolidating those, I think the video should start, yeah. Then you're starting to squeeze those together and we start to see this effect, for instance, of nesting of the smaller weight of tow into the larger tow here. So we're able to predict the microstructure of our material during the processing. And then we could implant that into an abacus model of the mechanical properties, which show here, where we can vary things like volume fraction of the fibers and matrices to give us a prediction of elastic performance. And we also can take that model as an electrochemical model. Okay, so that's kind of where we're going with things. Now the problem is, you do this in abacus and you do this in COMSOL. And ideally, we'd like to have the two talking to each other. So the sort of problem that we'd like to solve is that you've got a mechanical model, you introduce damage. What does that do to the electrochemical performance? So moving that between codes is going to be quite cumbersome. We'd like to have, and I think industry would like, a single code that captures everything and allows that sort of coupling between mechanical and electrochemical aspects. So that's an aspiration we have for the modeling. And then, yeah, that's going to allow us to design structural elements. So where we've taken that is we've done some elastic modeling as shown here. I'll skip over this quite quickly. And also the electrochemical modeling we're working on. So the electrochemical modeling, Abacus has just introduced a battery model into the code, and we're now starting to explore using that for electrochemical model. And as I said, one of the aspirations there is to allow for damage and things to be introduced. These are some of the governing equations, but I wasn't going to dwell on these. But what we're trying to do is take that battery model and see if we can apply it to a supercapacitor model. And do that by manipulating some of these constitutive laws to allow us to do that. But no one's really tried to do this before, to take a mechanical material and explore it electrochemically. And there are some challenges here from the modeling perspective that I wanted to kind of dwell on here. First of all, the length scales are quite different. So the carbon aerogel, the actual porous structure is the order of 10 nanometers or so. So you've got a really fine microstructure in your electrode, but in your electrolyte, it's the order of microns. So immediately you've got 3 decades difference in terms of the length scales that are there. We have a difference in the length scale in the actual physics that's going on as well. So as I mentioned before, most of the charge is stored at this double layer between the electrode and the electrolyte, which is the order of a nanometer in scale. But then if you're looking at mechanical modeling of the material, it's a mesoscale problem. That's in the sort of length scale domain. We also have an issue in the temporal domain as well. So batteries happen over a sort of long period of time, so you might be able to get away with a relatively stable model. But with supercapacitors, we're looking at very high changes in voltage with time. So it's a transitory process. So the modelling needs to capture that rather than the sort of steady state which the Abacus module already does. And also there's actually a lack of 3D models. A lot of the models that are out there for electrochemistry are just 1D or 2D models. And because of the microstructure of our material and the anisotropy of our material, we need to have 3D models to be able to capture that. So we are just embarking on this. This is Shiming, a PhD student, and she's looking at trying to do stuff in the mesoscale and macro scale. And this is really looking at coupling the electrochemical analysis with the mechanical analysis. But then if you move to batteries, you have an added complication of the thermal analysis to worry about as well. So that makes it even more of a challenging problem. And she's looking at sort of the nanoscale modeling of this and looking at see what she can learn from the battery model to take that forward. Let me skip on to the sort of final theme, which is focused on some of the sort of scale-up issues associated with this technology. So current collection is something that I've touched on before, and this is quite a difficulty for us because with the supercapacitors, everything is driven by how quickly you can deliver the energy. And with conventional devices, what we have there is we have a current collector, which is a metal film, and the electrode is then added to that as a powder, and there's a binder there that holds it together. But it's the current collector that actually supports as a scaffold for the active material. So the current collectors actually turn out to be quite heavy. They can account for about 25% of the mass of your supercapacitor, conventional supercapacitor. The advantage we have with our material is the fibers, the electrodes, are carrying the mechanical load. So the current collectors could be very, very thin. So this is something we're exploring. And really where this started to hit home to us was when we started to look at scale up our devices. So we took a swage lock cell, which is this 10mm diameter device, took exactly the same material, and we made an A4 sheet of material, and then looked at two different types of current collectors, either this current collector around the edge or having this grid, for instance, as the current collector. And we found that there was a huge drop-off in performance. The capacitance, so that's related to the specific energy, dropped by about half, and we could recover some of that by going to this copper grid, but that copper grid was heavy. But the power was really the big problem here, because the swage lock cell was giving us, say, about 2 kilowatts per kilogram. If we went to this size, we had this enormous drop-off in performance. And the reason for this is electrical losses in the system. So we've started, well, we had some work on current collection, where we started to model this, just using Abacus with the electrical model in there. We characterize the different resistivities associated with the system. So there is an in-plane resistivity, a through-thickness resistivity, a contact resistivity between the current collector and the electrode, and then the inherent resistivity of the current collector itself. And then this is showing you for different configurations of current collectors. So this is a side strip. You could put the strip down the middle. And in fact, if you do that, you actually get quite a saving in terms of reduction in electrical losses. And then started to play around with different configurations to give us different balances. So if I move on to this slide, which is showing you the percentage weight of the current collector against the resistive losses. So the higher this number, the more losses we're getting electrically. The copper tape we're using at the moment is 35 microns. But we recognized if we could actually make that down to 5 microns, then we'd, rather than having almost 10% of the mass, it would just be less than 2% of the mass of the device. So we could get a weight saving without getting any significant increase in the resistive losses. So there's some strategies here that we could recognize that could start to give us improvements in the current collection without adding lots and lots of mass to the device. And then the final challenge is to do with encapsulation. So we've made the device, and but it's electrically active, and the electrodes and the electrolyte are exposed to the atmosphere, and they shouldn't be. So we need to encapsulate it in something. So the first thing we thought we'd do is we'd sandwich it between 2 layers of glass fiber prepreg. But what we found is that that glass fiber prepreg sucked out all the ionic liquid and killed the device. So we're now working on strategies to identify encapsulation solutions which will resolve this particular issue. So those are 2 aspects that we need to take forward from the engineering point of view, but there's a whole issue of ownership issues associated with this technology before industry will actually take it on board. So fabrication and scale-up of these devices is going to be important. Machining, as I mentioned before, drilling holes in it, which is what we like to do as composite people, but not what we want to do as battery people. There's a durability aspect. So impact, fire is going to be really important. So fire resistance, if we're looking at cabin applications, as I've alluded to, cabin applications is really where we see this technology going. Then designing these materials to make them fire resistant is going to be important. So that's something that we're focusing on. Long-term performance, so looking at thousands of cycles and how the degradation of the material is. Service temperature, and then of course repair, recycling, inspection. These are all things that, as the material technology is moving forward, we need to resolve these to get industry to take them on board. So I just want to finish on the sort of this theme 4 by talking about some of the demonstrators we've made. Because demonstrators, as an engineer, are a really good tool for trying to get interest from industry in these technologies. So we had a project called Storage, where we're working with Volvo, and the first step in that was to embed batteries in a carbon fiber structure. So we used the plenum cover, which is essentially at the bottom of your windscreen you have a bit that basically where the leaves collect. And at the moment that's just a polypropylene structure. What Volvo suggested doing was to take the start-stop battery out of the engine compartment. So that's the start-stop battery is when you get to the traffic lights, the engine cuts out and the systems on the car, like the air conditioning, is run by that battery. They took that battery out and they put lithium-ion batteries into the plenum cover. So they found a weight saving associated with that, which is quite significant. They also had a volume saving because they no longer needed a battery in the engine compartment. But what they also found was that because you no longer had the battery in the engine compartment, you didn't need to cool the engine as much. So there was a thermal saving as well. So although making this sort of carbon fiber lithium-ion battery hybrid was quite expensive, they actually recognized that the mass savings, the volume savings, and the energy savings would be significant by going down this route. And they were very keen to see this technology in use, so they actually put it into a car, drove it around Gothenburg for 18 months, and it worked fine. And it rains a lot in Gothenburg, so that didn't prove to be an issue for this, which was something we were worried about originally. But the more advanced aspect we did was we made a boot lid. So again, from a Volvo S80, we made this boot lid component where we incorporated the structural supercapacitors. There were 16 cells into the structure of the boot, so it carried some of the mechanical load and allowed it to power some of the energy systems like the light in the boot. So this is again this localization of energy storage. And again, we've got that Imperial in the lab. It's from 2012, I think that is, and it still works, which is very encouraging. And then more recently, we had an EU project called Sorcerer, which was focused on an aerospace application. So if you get onto an A380, look at the door on the A380, there's this big block on the door, and that's a bank of supercapacitors. There's 53 supercapacitors. And those are there in case there is a power surge, there's a heavy landing, the door gets jammed, that supercapacitor bank produces enough torque to force the door open for you. So it's a added weight, And what we thought we'd try and do was make a structural beam, a fuselage beam, that was using structural supercapacitors to replace that component. So we designed the component, we made a little demonstrator as illustrated here, and these are the individual cells, and then you can see the current collectors on there, but we hadn't solved the encapsulation problem, so they're in these sort of coffee bags, which is the conventional conventional encapsulation solution. And then we've built this sort of meter-long C-beam, which includes those structural supercapacitors, and we've used that to power this, this door. Okay, so I just want to finish off by talking a bit about research strategy, and then sort of talk about what are the sort of wish list from what I'd like modelers to do to take this technology forward. So kind of see this as an opportunity for areas that we see modelling input is needed to take this technology forward. So in terms of strategy, we've kind of thought a lot about what are the sectors that could take this technology forward. So aerospace, I've talked about a lot, automotive and portable electronics potentially. We kind of see a big opportunity with micro-mobility, so that's scooters, so e-scooters, e-bikes, those sorts of things. So some of the things we've been exploring is could you make the frame of the bike out of our material to drive the sort of GPS and things like that on your bike. So these are sort of transportation, lightweighting aspects. Medium term, these things like robotics, drones, defense, the environment there is a bit more sort of extreme. So higher temperatures, more issues with damage and things. So that's probably a medium term focus. And then the longer term, we kind of see things like marine, construction, space. A lot of these are really driven by volume of material, so costs become important. And then space, one thing we think is a potential issue for this technology is the temperature. Batteries don't like being at high or low temperature, and our materials would be the same. But now let me just finish off talking about the themes, the areas that we feel that modelers could make a contribution to. And again, remember this sort of micro, meso, and macro structure to what could be achieved. So I've broken this down into the themes again. There's 4 themes that I spoke about. And first of all, starting on the constituents, we think there's an opportunity for discovery of new multifunctional constituents. So the topology optimization is what we've used already to come up with these microstructures, and we've 3D printed these. We focused on electrolytes, but there could be opportunities for modeling the electrodes, for instance, using topology optimization. So for instance, the electrodes need to have very high surface area and carry mechanical loads. So there might be opportunities there for doing sort of multifunctional optimization of that route. And then interfaces. So again, the interface needs to carry mechanical load and allow ion transport. So there's a sort of sort of optimization problem there, where you're looking at several conflicting objectives and trying to optimize for those. So again, opportunities there. And I think there's an opportunity to move away from the sort of planar structure that we have in conventional composites and batteries. Because one thing that I feel that we could live with a soft electrolyte if we could have an interface which is not planar. If we have a sort of interlocking interface, which you had a soft electrolyte within that interface, then the actual interlocking of the electrodes could carry the mechanical load, while the soft electrolyte could provide the ion movement. So I think there's opportunities there, perhaps looking at bio-inspired structures. So nature tends to use very non-planar structures to make things much more tortuous and provide routes to getting multifunctionality. So that's at the constituent level. I think there's opportunities in process modeling for these materials. So we've done a lot of work on mixing the ionic liquids with the structural epoxies. Other groups have used other types of polymers. The issue there is that there's a strong chemical interaction between the ionic liquid and the structural phase, and so we're looking at how to optimize that. And I think modeling, process modeling, flow modeling, and drape modeling as areas I think could be useful there. Modeling new architectures, so there is an existing body of work at looking at battery modeling and supercapacitor modeling, bringing those together to come up with more challenging device architectures, hybrid ion capacitors, and also the thing I mentioned earlier about the balancing of the cells, so mechanical and electrochemical balancing at the same time. And then I think, as I mentioned about protocols, we really need to have a coupled mechanical electrochemical test. So this is something that people at KTH had developed at a very small scale. This is a bundle of carbon fibers in an electrolyte. They basically took their fibers, applied forces to them while taking voltage measurements or applying voltage to that. And that all had to be bagged in a encapsulation material to stop the electrolyte leaking out. But I think there's opportunities there for coming up with using modeling to really help inspire the development of a coupled test. And so in order to develop multifunctional data, we need to have that sort of coupled test. Theme 3, on the modeling side, I think there's big opportunities in multiphysics modeling. So that's melding conventional composite models with electrochemical models in a single code. And I think industry is not going to accept, I'm doing my electrochemistry in COMSOL, I'm doing my mechanical modeling in Abacus. They want to have one standalone package that will do everything for them and capture the coupling processes. So that, I think, is an aspiration, getting those two codes to talk to each other and actually form one code. And that's going to allow us to do sort of elastic behavior, strength prediction, defects and damage. So all these things are very mature in composites, but no one's tried to do this in our multifunctional materials. And ultimately, the delivery of sort of virtual testing, virtual certification tools will be important. And then another thing on the modeling side is the multifunctional design tools. So this is the question, I've got a multifunctional product, I've got a battery plus a structure, which one is superior? Which one offers the better weight saving? And so at the moment, we have very rudimentary tools for making that comparison, but I think these need to be advanced. They need to incorporate the predictive models, the multiphysics models. They need to incorporate the life cycle assessment models as well, because the whole point of doing this is to reduce the environmental impact. And so we need a life cycle model in there as well. And that's really going to help us understand how we have ownership of these materials, so repair and inspection, and even end of life. So can we recover, can we recycle these devices? And then the final aspect on theme 4, I think we've already started working on using modeling to optimize the current collection configuration. I mentioned about fire, and I think there's opportunities on modeling the chemistry that goes on during fire. My colleague Ajit said I should suggest using fast marching as a methodology for achieving that, although I don't know what it means. And so this is something we need to address from the point of view of getting this material into cabins. And modeling of multi-cell assemblies. So if you make a single device, you can characterize that. But ideally, a single device is not going to be enough in a final product. Aerospace, we want to achieve about 24 volts minimum in our product. So we would be looking at using about 10 cells. But what if those cells are slightly different in their performance, or one of those cells dies partly through its life? How do we design our component? And again, opportunities for modeling with that, I think. Okay, so I'm just going to finish now and just sort of run through what I've covered. This is a really exciting technology. Having come from a composite background, the downside of working in this area is I find composites quite dull now when I go back to looking at that other research that I do. It's trying to bridge these very disparate fields. So we're trying to work with electrochemists and composite mechanics people, and that is really interesting to be in that space. The devices are getting good performance. We're kind of at TRL 3 or 4 at the moment with this technology. But there are some things that we need to still do. We need to deal with the interfaces and the electrolytes. We need to develop protocols for characterizing these materials and reporting these materials. We need to deal with current collection and encapsulation and the predictive tools as well. So we kind of see aerospace as the key aspect that we can focus on here in auxiliary applications rather than powering the aircraft. But we really kind of think that this is such a simple idea. Having a material that does two things at the same time is clearly going to offer benefits, and as engineers it offers us design freedoms as well. So we feel it's a case of when this happens rather than if it's going to happen. We think in 5-10 years, we will be using structural power materials in our products. So I just want to finish by acknowledging my colleagues that have worked in this area with me and our funders in this area. And a final thing I just wanted to flag up is that as part of my fellowship, I've arranged a showcase event to industry. And the idea is to convey this technology to industry. That's on the 10th of June. It's just a half-day event, it's free. And the idea of that is to really convey this technology to industry. This is the schedule for the event, and these are some of the speakers. And so I think for the first time ever, we've got all the leading people working in structural power from across the world together in the same room. So we feel this is going to be an opportunity for industry to really understand this technology and things. Okay, so thanks for your attention. Great. Any questions at all? Yeah.
Sure, there will be plenty of questions. Who wants to go first?
Yep.
I'm just wondering, because I'm not sure if I caught that. When you have the structural electrolyte, because you mentioned that you need to work on the strength of it to increase the strength of the whole composite. But does it also introduce issues like delamination, or is that something that's comparable to conventional?
I've worked in delamination most of my career, and with this, it is a problem we're going to have. It's just at the moment we've not got to the stage where we can worry about it too much. But it is a problem. I mean, we're focusing at the moment on the stiffness of the structural electrolyte because we see that as the big driver for actually adopting it. But certainly, goes back to the interfaces question, that those interfaces need to allow ion transport. So ideally, those interfaces should have no impediment for the ions to get to the electrodes, but they need to stop. They mustn't delaminate. So, and the way you do that is put a big, thick barrier of epoxy there. So, again, it's a conflicting requirement that we feel we need to try and look at sort of outside the box, really, for solutions to achieve that. So this is the idea of using bio-inspired materials.
Yeah, but you're not even at the point where it's for you.
Sorry, say again?
But you're not at the point where it's...
Not yet, no. But I mean, I think we're going to end up going to non-laminar type configurations where delamination just won't happen because there's no planar interfaces, basically.
How interesting is it to take it to large deformations or moderate deformations? If you develop that, can you store more energy? Is it interesting or not?
With the structural supercapacitors, there's no change in the electrochemical performance with deformation. They're completely uncoupled, as long as you're in the elastic regime. With batteries, there are some really interesting things that happen. When you go to large deformations, the electrochemical characteristics change, and you can start to exploit that through sensing, actuation, and even energy harvesting. I'm not sure the energy improves the storage, but we did wonder that if we stretched it, would we get a contraction so the electrodes were closer together, but that didn't really seem to manifest. So with what we've been looking at, there isn't any advantage going to high deformations and things. Yeah.
What are the costs per watt storage of your devices?
I have no idea. Because everything's moving quite fast in terms of the technology. it's difficult to put a cost associated with that. What we see is that if we can get to certain energy levels, we're going to achieve double the range of the vehicle for the same amount of energy being stored and things. So the ownership cost, sorry, the costs associated with ownership and certainly the sustainability associated with ownership are going to be tremendous. They're really going to be good, attractive. The material itself, I think part of this is that in order for you to go from A to B, at the moment, if you have a car, 25% of that energy you've got is actually moving the batteries around, so you need more batteries. With what we're doing, the vehicle is lighter, those materials are doing two things at the same time, so you actually would need less material to achieve that particular journey. So we think, you know, that we need to explore this more, but we certainly feel that the costs are not going to be too much of an issue in the longer term. And there's also the fact that these materials will potentially offer huge sustainability benefits, so that would help in terms of making them attractive to industry, I think.
Oh yeah, at the moment you're just experimenting with playing with carbon fibers as like electrodes, if I understand.
We're putting carbon aerogel onto them, yeah.
So that's the continuity. Did you try with something like doping them with something like more conductive elements, like methanol, something like that?
Yeah, we've done some work with manganese dioxide to get pseudocapacitance, things like that. We're very aware of weight, so anything that goes into it, we want to make sure it doesn't add significant weight, because we've been driven by weight rather than volume. So we've not looked at any sort of doping of metallic components or anything like that. But certainly that's where we're going to be going in terms of getting pseudocapacitance using the metal oxides and the chalcogenides to achieve that, I think. The battery people are using lithium-ion chemistry with what they're doing in Sweden. And they have looked at other types of, they've looked at sodium-ion and potassium-ion devices. But I think the intercalation of the lithium ions into the carbon fibers is better is better than it would be for sodium or potassium, basically. They can't get the energy densities with sodium and potassium. Yeah.
You explained the power composite, this very powerful concept, and you naturally, if I understand correctly, settle down with a specific approach which relies on supercapacitors instead of the battery approach. Is this now already a general consensus in this field of power composite, or this is one of the approach you have taken?
Yeah, I mean, it's the approach that we've taken. We pioneered the supercapacitors, and now more people are doing that. There's quite a body of work on structural supercapacitors, as I sort of showed in that review. The battery work, the Swedes have led that, and again, there's bodies of work in that. I'm not aware of many people having done hybrid devices, which is what we're now embarking on. So that's with a battery electrode and a supercapacitor electrode. By bringing those together, you should be able to get 4 times the energy density for the same power density in the device. Although the chemistry is quite challenging, I think. But yeah, it does fall into supercapacitors and batteries. There was some very early work in the US and in Sweden on electrostatic capacitors, basically using carbon fiber electrodes with a separator layer. But the energy storage is not very high with those, so it's only useful for high energy weapons and stuff like that and things. So yeah, batteries and supercapacitors tends to be where most people are sitting with this. Yeah, those are the 2 types of device. Yeah.
Antonio, maybe we'll make this the last question.
Can I ask another question, if I may?
Yeah.
I got lost, but anyway, I'll ask you another one. Going back to what I said before, that for you there was no interest in large deformations. Then, regarding the coupling slide that you presented,
Yeah.
what sort of coupling then do you foresee between the mechanics and the electrochemistry? I understand it now when you incorporate the thermal effects, indeed.
Yeah.
But between mechanics and electrochemistry, is there any coupling in between that you foresee, for which you need a unified platform?
Well, I think from our supercapacitors perspective, It's when you go beyond the elastic regime. So if you get damage, what does that do to the electrochemistry? And similarly, if you get aging or degradation from electrochemical performance, has that changed its mechanical properties? I mean, having come from an aerospace background where everything is focused on this Rouchon pyramid for certification, I kind of envisage with these materials you actually have another axis where you've got the electrochemistry in another dimension of that Rouchon pyramid. So I kind of feel, as an aerospace person, we need to have modelling that does the sort of virtual certification to allow us to get this onto an aircraft, basically.
Okay. Thank you very much.
Okay.
Offer a kind of a vote of thanks. I mean, whenever we have these research seminars, it's good to have opportunities to be provoked, be inspired, and also to be challenged. I think you've had all three of those. I could sense as you were going through those and hearing the challenges for modelers, I could almost hear you formulating your grant proposals. So let's thank Emile one last time.
Thank you.